So today's lesson is more about scale drawings, and it's again this bottom thing, the last standard in this group before our test. Today we're going to be talking about finding areas from a scale drawing. So yesterday we were doing length and how when you have a scale drawing how you can find a missing length. Today we're going to be talking about area. So the first thing says use the diagrams below to find the scale factor and then find the area of each figure. We're going to do example 1 together, and then I'm going to have you guys work on examples 2 and 3 on your own. Okay, so to find the scale factor, how do we find the scale factor? What do we do? Ava.
Y over X.
Y over X. That is the right answer, Ava. Y over X. So if you think about when you're talking about scale factor, it's just like when you have a table, how you have X on the left, Y on the right. We've got the actual picture, the scale drawing. So we're going to call this X. We're going to call this Y. So to find the scale factor, we do Y over X. What has to be the same in order for us to find the real scale factor? Fine.
Scale drawing will always be Y?
Yes, the scale drawing will always be your Y. Okay, what has to be the same in order for us to find the scale factor? Eva? The units have to be the same. And in this case, they are because we're using the same grid. So we're using, it doesn't even tell us what the units are, but the units are basically the squares on the grid. So since the units are the same, we can find a scale factor. Chris, what would the scale factor be for that picture?
1.5.
No, what did you divide to get that?
6 divided by, oh, I didn't know.
You see what to do now? What would you divide to
6
find?
divided by 3.
Yes, you want to divide corresponding sides. So you could either do 6 divided by 3, or you could do 8 divided by 4. And what do you get when you do that, Chris? 2. So your scale factor is 2. If the scale drawing is larger than the actual picture, your scale drawing is going to be greater than 1. If they were the same size, your scale drawing would be 1. If the scale drawing were smaller, your scale factor would be a fraction. So keep that in mind as you do examples 2 and 3. You have scale drawings that are smaller, so you're going to expect to get a fraction. Okay, now it asks for the actual area. So we're going to go to this actual picture. What is the area of this rectangle? Let's see. Charlie, what's the area of that rectangle? 12. 12, and we'll say 12 units squared. If you put a little 2, that means square units, and that's what we're measuring it in. We're counting the number of squares that make up that picture. Okay, on the scale drawing, Jack, what is the area of the scale drawing? How do we find the area? You could count all the squares, but what's a quicker way of counting all the squares? Katie?
You can do 8 times 6.
Yeah, if we do length times width, that gives us the area, because we're saying we have 8 rows with 6 squares in each row. Mine looks a little off because yours looks more correct than mine. My squares look like rectangles, but 6 squares, 8 rows of 6 squares is 8 times 6, which is 48 square units. Okay, what is the ratio of the scale drawing area to the actual area? So the ratio of the scale drawing to the actual. Tessa, what's that ratio?
36.
No? If we take, I think you're thinking about subtraction maybe. This scale divided by, it would be divided by actual. We take the scale drawing area, which is 48, and we divide it by the actual area, which is 12. What do we get? 4. Good. So the value of the ratio of the scale drawing area to the actual area is 4. How does that compare to our scale factor? Is it the same? No. So you can't use the scale factor. You couldn't figure out that this picture was 12 square units and just multiply by 2 to get the area of this. It doesn't work. Okay, so we'll talk about what does work after you guys do examples 2 and 3. So examples 2 and 3, and then you can start to answer the questions too where it says results, and that's what we will be talking about. Okay, so for example 2, let's see, Ellie, what did you get as the scale factor? Good, 1/3. Did you all get a fraction for the scale factor, or did some of you get mixed up and write 3?
I got 3.
It's not 3, because the scale drawing is smaller than the actual picture, so the scale factor has to be a fraction. If we do y over x, the actual is always going to be x, the scale drawing is going to be y, just like in a table. You can set it up the same way. 3 divided by 9 is not 3. 3 over 9 would reduce to 1/3. Connor, what did you get as the actual area?
6.
The area of this picture?
Oh,
The actual,
54.
yeah, 54.
I got them mixed.
So 54, and we'll write square units. Okay, and then Connor, you already told us the scale drawing area is 6, so we'll just go with your answer from that. So 6 square units. What is the value of the ratio of the scale drawing area to the actual area? Other Connor? 9. Good. Okay, example 3. Kaden, what is the scale factor? 1 1/3, good, and you would expect to get 1 greater than 1 because the scale drawing is larger than the actual picture. So 1 1/3, or if you put 4/3, that's okay. I'm not going to have you always need to change them to mixed numbers, so 4/3 would be fine there too. Actual area, Andrew.
I didn't know how to do it.
Okay, so for a triangle, let me write that area again. It's area equals 1/2 base times height. So this is the base of the triangle. This is the height of the triangle. So you're going to take 6 times 9, which is,
54.
and then half of that would be the area of the triangle. 27, good. So the actual area is 27. The reason this works is if we extended this triangle like this, we would have 2 identical triangles fitting together to make a rectangle, right? So if we found the area of that rectangle, we would just do 6 times 9, and then each triangle is half of that. So that's why that formula works. It's kind of helpful if you know why they work, so that if you forget the formula, you can reason through what you would do. Okay, the scale drawing area, Allie.
I got 48 units.
Good, 48 square units. Got 25 up here. Okay, and then the value of the ratio of the scale drawing area to the actual area. Ava. 1 7/9, yes, or 16/9. 1 7/9. Okay, now, in the results, let me see if I put this up here. Yes, I did. What do you notice about the ratio of the areas in examples 1 through 3? Complete the statements below. So when the scale factor of the sides was 2, as it was in example 1, Kate, what was the value of the ratio of the areas?
I would
We'll just do it now. So just look back to example 1. So when the scale factor of the sides was 2, the value of the ratio of the areas was? Just look back at example 1. What did it say the value of the ratio of the areas was? Did you write that down? Yeah. So it's when we found the ratio of the area, the actual area, to the scale factor area. That's what we're looking at here. Okay, when the scale factor of the sides was 1/3, Bryce, what was the value of the ratio of the areas? Did you get this? Did you write it down? No? Eva? 9. No, it wasn't 9. It wasn't 9.
What are we supposed to look at?
Did we say it was 9? If we did, it was wrong. We did say it was 9. It's not 9. If we take the ratio of the scale drawing area to the actual area, sorry, we need to go back here. It's 6 over 54, not 54 over 6. What does that make the ratio? Emily? It's 1/9. Yeah, sorry about that. I missed that. Okay, so that's 1/9 because it's smaller, right? The area is smaller, so it needs to be a fraction. Can't even blame that one on Monday. Okay, so the actual area was 1/9. And then when the scale factor of the sides was 4/3, they're keeping the improper fraction here because it's a little easier to see. The value of the ratio of the areas was, Sammy, what was the value of the ratios for example 3? Good. What was that as an improper fraction? Can you change it to improper? Because that'll be easier to see.
16.
Good. 16 over 9. Okay, now I want you to look at the scale factor of the sides and the ratio of the areas for each one of these examples. And it says, based on these observations, what conclusion can you draw about scale factor and area? Do you see any pattern between what's going on for the scale factors and what's going on for the ratio of the areas? Ava sees it. Does anybody else see it? Okay, Emily sees it. Anybody else? Katie maybe sees it. Okay, Katie sees it. Good, we're just getting a few more people who see it. Okay, let's see. Caden, tell us what you think.
So it's like multiplying it by itself.
Multiplying it by itself. Good, good. So if we multiply 2 by itself, 2 times 2 is 4. If we multiply 1/3 by itself, 1/3 times 1/3 is 1/9. If we multiply 4/3 times 4/3, we get 16/9. That's called squaring. When we multiply something by itself, we square it. So the ratio of the areas is the square of the scale factor. And if you don't know what the square means, then you should explain that this means when you multiply it by itself. When you multiply a number by itself. The reason they call that squaring is when you find the area of a square. Square has sides that are all the same length, so you're multiplying the number by itself when you find the area of a square. So we call that squaring when we multiply a number by itself. Yes? Yes. Yes, when we write units squared, we could write this as, we can say 2 squared equals 4. That means 2 times 2 equals 4. And we'll learn more about that when we get into our unit where we do some of that. So 1/3 squared means 1/3 times 1/3, which is 1/9. 4/3 squared means 4/3 times 4/3, which is 16/9. So we can say if the scale factor of the sides is R, then the ratio of the areas is R squared. Just kind of a general, very mathy sounding sentence where we use a variable to represent the scale factor of the sides. So whatever the scale factor of the sides is, we just multiply that by itself to get the ratio of the areas. Okay, so think about this. Suppose you have a rectangle, and the rectangle has an area of 12 square meters. Maybe I should actually draw this. This might make more sense. Let me draw it. Okay, so say we have a rectangle, We don't know what the lengths of the sides of this rectangle are, but the rectangle's area is 12 square meters. If we were to enlarge the rectangle by a scale factor of 3, what would be the area of the new rectangle? So we're going to have this, it keeps going because I can't draw it. So we have this new, that's not even 3 times. That looks terrible. Let me just redo that. Ah, not what I meant to do. I should have started with a really small one. So let me start with one that's, let's see, that would be 1, 2. Okay, and it would keep going off the screen so we can't see it. So we have this new rectangle. What would be the area of the new rectangle? Andrew?
36 meters.
No?
Or 130.
No, would not be 36 meters. Because what did we just learn about the scale factor or the ratio of areas? Is it the same as the scale factor?
No.
No, it's not the same. So we can't just multiply the area times 3. Okay? We would need to multiply it times 9. That would be the ratio of the area. So what would the area of the new rectangle be then? 108. Yeah, because we would have to multiply 12, not times just 3, but we have to think 3 times 3 is 9. So the area is going to be 12 times 9, which is 108. Let's try another example like that. Let's do, I'm going to start smaller this time. I'm going to draw a triangle. And I'm going to say that the area of this triangle is, let's say it's 8 square inches. And then I'm going to make a new triangle. And I'm going to say that my scale factor is, well, let's say 4. My scale factor is 4. What would the area of the new triangle be? I'll give you a second so you can all think about this.
Is the smaller triangle the X or Y?
The smaller triangle would be X. Emily? It would be 128. Good. How many of you had that number in your head? 128. Okay, good. Emily, can you explain why?
I did 4 times 4.
Mm-hmm.
And then I did that 16, and I did 16 times 8.
Okay, good. So we can't just multiply 8 times 4 because it doesn't work that way for area. It only works that way for length. We have to square the scale factor. So 4 times 4 is 16. 16 times 8 is 128. So the area of this triangle would be 128 square inches. Okay, I'm going to put another one up, and I'm going to use the cards to pick someone to give me the answer on this one. We're going to do, you have a question?
Yeah, I thought for triangles you had to like divide by 2 on area.
You do when you find the area, but we already found the area here. It already gave us the area, so we didn't need to do that. You could take the area of any bizarre shape. In fact, we'll do the area of a shape that's not even a normal shape. We'll do the area of a house shape. Okay, so we'll make this little house, and we'll say that the area of this house is 4 square inches, and then we will draw another house. We will say that the scale factor is 2, and then we need to find the area of the new house. Okay, I'm going to use cards on this one, so everybody needs to at least do this in their head.
Should have done a harder number than 2.
Yeah, I know, but it's getting the idea of how to do it, so we don't need to have hard math on this one.
Can I get the doctor?
It's an emergency. What did it just say? Haley?
16.
16, good, good. So explain how you got 16.
You need 2 times 2 is 4.
Mhm. Good, so we have to square the scale factor. 2 times 2 is 4. And multiply that times the original area to get the new area. How many of you had 16 in your heads? Good, good. You guys are getting this much better now. Okay, now let's move on in our lesson. Oh, there, I had it right there on my screen. I forgot that I had it there. Okay, example 4. They said yes. Okay, the student government liked your half-court basketball plan. Remember that problem from
I
yesterday?
thought it was the same.
So yeah, it's similar. Now they have asked you to calculate the actual area of the court so that they can estimate the cost of the project. Based on your drawing below, what will the area of the planned half-court be? Okay, so just like we did for the other problem, we're going to set up a table. So we're going to have, let's start with the scale drawing on the left. And let's do the actual over here. It'll just make our calculations a little bit easier. So it says that 1 inch on the drawing corresponds to 15 feet of actual length. So we're going to keep this in inches and feet, which we can do. And we know that this is 2 inches. We know that this is 1 2/3 inches. So let's be reminded of what our actual measurements are. What would our actual measurements be? Ava?
30 feet by 2.
Good.
And then 1 and 2/3
Do you have that, Kate?
25.
25, yeah, and we found those numbers yesterday. Yesterday we did it differently, we put the actual on the left, the scale on the right. Doesn't matter which way you do it, as long as you're consistent in applying your constant of proportionality or your scale factor. Okay, so if we're gonna find the actual area, we could do this a couple different ways. We know the dimensions of the actual court from yesterday. So we could simply multiply 30 times 25, and that would give us the actual area. Or what else could we do? What did we just do today? What if we didn't know these units and all we knew was this? What could we do? Eva?
You get 15 times 2 and 15 times 1 to get those.
Right, to get these, but what if we didn't want to use these numbers at all? How could we use just these numbers to find them?
Use the bigger numbers. Easier, right?
Yeah, it is easier just to use the bigger numbers. But what I want to point out here is if we use the smaller numbers, which we could do, we could find the area of this. But if we did find the area of the drawing, could we just multiply that times 15 to get the actual area?
Yep.
No, because what we just learned was that the scale factor and the area ratio are not the same, right?
Don't multiply by 2.
Not multiply it by 2, multiply it by itself. So you would have to take 15 times 15, and that's what you would have to multiply by the,
That's a big number.
yeah, it would be a big number. So it's easier just to use these actual area numbers. So if we do that, what does it end up being? Tessa? 750 square feet. Okay, what I would like you to do now is, oh, wait a second, there's a question there. Does the actual area you found reflect the results we found from examples 1 through 3? Did I put that up there? No, I did not. Okay, so if we look at, let's actually do it the other way. If we do 2 times 1 2/3, that would be times 5/3 would give us 10/3. Okay, our scale factor, or our scale, it's actually a scale ratio, it's not a scale factor because we're going from inches to feet. So our scale ratio was 15. We would have to multiply 10/3 times 225, which is what 15 over 15 is, in order to get our answer. If we did that, let's see, 3 goes into 225 75 times, 10 times 75 is 750, so we would still get 750 square feet. I mean, obviously, it was harder to do it this way because you had fractions and such. The original was a lot easier to find. Okay, now what I would like you to do is I would like you to do exercise 1. You do not have to do exercise 2 because that one's kind of, just kind of tricky. So I want you to do exercise 1. I also want you to do from the problem set. We're going to do these in class. Your actual homework is going to be easier than what you have in here. So you're going to do exercise 1, number 1 from the problem set, and number 4 from the problem set.
Can you write it on the board?
Yep, I will. So exercise 1, problem set 1 and 4.
Can we do it with a partner?
Yes, you may. Exercise
No, Bella will.
1 and then problem set 1 and 4.